Hello, my name is Dan Ambray from Full Spectrum Diagnostics. Today we're going to look at a problem from the perspective of the vibration fault periodic table. The periodic table is a logical visual mapping system to understanding vibration as systems thinking. We start with a full table. There's 35 common rotating machinery faults. Our first step is to logically sort these faults for frequency content. This means we define how the fault relates to shaft rotating speed. For faults that are at turning speed, the fault is synchronous. An exact multiple of shaft speed, the fault's harmonic. A fault that is less than shaft speed is subsynchronous. If the fault is not an exact multiple of shaft speed, it's non-synchronous. And finally, the spectrum is pulsating. If it's pulsating, it might be due to amplitude or frequency modulation. Our second sorting mechanism is the dominant directional response. Red blocks on the table indicate a radial fault, yellow blocks indicate an axial fault, and orange blocks can be either radial or axial. And finally, we perform a diagnostic test as indicated in the upper right-hand corner of each block. Our tests are going to be phase analysis, time waveform, orbit analysis, transient analysis, and ultrasonic analysis. Okay, so let's get started here. We're going to take a look at our machine. It's a rotary screw compressor. It's driven by an electric motor. It's a 4-pole AC induction motor without a variable frequency drive. The turning speed is 1784. The motor has rolling element bearings. The compressor has rolling element bearings. And the ratio is 3:4 for the lobes in the blower. The dominant frequency grouping is defined by the peak in alarm at position 4. We look at all this data that we take in, positions 1, 2, 3, 4, axial, horizontal, and vertical. We dump it into our database. It compares it to the alarm criteria, which is the red stair-step profile. And we find peaks that are not related to or not in alarm, and it allows us to better understand what the frequency group is. So in this case, we find a peak at positions 4 in the horizontal and vertical directions, and it's at 3.049 times RPM. So it's not at 3 times or 4 times. It's not an exact multiple of shaft speed. It's a fraction. And that's usually an indication of a rolling element bearing problem. We're going to take a peek at this, and one of the easy ways in your database is to put a harmonic cursor on your running speed. So my 1784 rotational speed, I put this square harmonic cursor on there, and I can see where it lights up. So there's a peak right next to our fault, our issue at 5441. This peak is 3 times, this peak is 4 times, okay, and ours is in the middle. Okay, so we're going to take a look at that and try to see what could be causing it. So we've determined that our fault is non-synchronous, and there's 10, 15 different faults that this could be. There is no color coordination, either red or yellow or orange, that's going to help us here, but there are a lot of peaks that this will not apply to. So we're going to walk through what it can't be based on the configuration or frequency content. So frequency grouping, it is radial, horizontal and vertical, so that's showing up, and it is at position 4. There's rolling element bearings at that position. So if we want to sort by directional response, the only thing that can help us is the red is radial. So we'll see what else is in here. There's an axial fault, which is the fundamental train frequency or the cage frequency of the rolling element bearing in the compressor at position 4. However, the signature of the cage frequency is subsynchronous, not non-synchronous. Okay, so it's in the wrong place to be applicable here. We can eliminate non-applicable faults due to design. So we have oil whip and oil whirl. These 2 blocks here don't exist because we have rolling element bearings. There's no belt drive, so we can get rid of belt frequency. Electrical pole pass, electrical DC motors, and electrical line frequency can go away because this is a compressor problem, not a motor problem. Turbulent flow might be a possibility, but there's no broadband random noise, so we can get rid of turbulent flow and cavitation. And last, we have barring, which is a paper roll type issue found when two big rolls are in contact with each other. We don't have that geometry in this piece of equipment. So what are we left with? We're left with an outer race defect on our rolling element bearing, a ball spin defect, inner race defect, a bearing natural frequency, and another structural natural frequency. Okay, so we've eliminated quite a bit. What we have left is a transient, and we're going to take a look at that first, and then these four faults can be are all the same as far as ultrasonics. We'll be able to pick out which fault is which in the ultrasonic signature. We have a peak, and it's very close to 3 times running speed. So we shut the machine down, we impact the structure in the axial, the horizontal, and the vertical directions. We look for a driving frequency right around 3. We have 3.1 something, 3.04, I'm sorry. So it should be in this range. Here in the axial direction, it sits in the gully. In the horizontal, it's in the gully too, and so it doesn't appear that we have a resonant amplification. The ultrasonic diagnostic test is going to give us an ultrasonic profile, and this is from your vendor. You can have peak view, you can have acceleration enveloping, you can have spike energy. It all depends on what the vendor's little sub-program is that calculates these things. But ultrasonic data is commonly taken in all route forms. So we're going to take a look at this, and I have some examples at the bottom, and this is more of a graphic that helps you understand what it could be and what it probably is. Okay, so I can hit random noise floor, and it's usually turbulence or lubrication type fault. There are no discrete peaks showing that bearing frequency. This is synchronous or harmonic mechanical looseness. So a mechanical looseness type C can usually have harmonics that extend pretty high in the frequency range and get into the ultrasonic range. These would be harmonics of 1 times RPM. And we don't have that type of fault. We have an actual non-synchronous fault. So the non-synchronous rolling element bearing fault appears to be the one that's showing up. And I got a ball spin here. So ball spin frequency, if I put my cursor on here and found that frequency and divided by running speed, it would be that 3.04 peak. Okay. And the last thing is non-synchronous and electrical. So we're on a compressor, we're not on the motor side, but if we were, we might see multiples of 2 times line frequency showing up in the ultrasonic spectrum. So in this case, it's probably a rolling element bearing fault, and it's probably ball spin. And that typically will statistically put you in the correct frequency range for this. So everything else goes away. The only thing left standing is ball spin frequency. It's very likely that fault. Or if there's some other strange occurrence, I don't see it. So it seems pretty straightforward in this case that we have logically sorted to the probable root cause.